Physics Notes, Unit 23, Electromagnetic Induction. It's a big fancy word basically for making electricity. If we were in class right now, I would ask everybody who likes electricity, raise your hand. And of course, everybody would raise their hand. We like electricity. I mean, it's the basis of all our electronic devices, our computers, our cell phones. We have wireless devices, but inside they are powered by electrical currents and things like that. But how do we make electricity? It's actually very simple. You need a coil of wire or some wire and a magnet. Before I get ahead of myself, let's just review a little bit. Magnetic induction, that was the last unit. What that means is, how do we make magnetism? Or the big question I kept asking you in Unit 22 is, where does magnetism come from? Well, magnetism comes from a moving electric charge. A moving electron or a moving proton or moving electrons in wires, same difference, or even a spinning electron, that creates magnetism. That's called magnetic induction, creating magnetism from an electric charge, inducing or creating or passing on magnetism. So now, this other word sounds a lot more fancier, electromagnetic induction. It's the opposite effect, okay? It's the process of creating, technically it's creating voltage or potential difference. Voltage, electricity by changing the magnetic field around a conductor or a wire. Like I say, it's the opposite effect. In other words, magnetic induction is making magnetism from moving charges. Electromagnetic induction is making electricity from a moving magnet. All of this has to do with something moving. So to make magnetism, you have to have a moving charge. To make electricity, you have to have basically a moving magnet, or the relative motion of a magnet by a conductor. Now, voltage is technically more basic, more fundamental than current. You have to have voltage before you have current. In other words, you can't have current without voltage. You can have voltage, potential difference, without current. For example, a battery is a good example. A battery, it's not being used, has a potential difference, but it's not providing current yet until it's hooked up to a conductor. So once again, though, this idea of motion is very important. Now, as I was saying, making electricity, not that hard. Electromagnetic induction, you need a coil of wire. Here I have, I don't know if you can see it, this is some heavy-duty wire. One loop. And the more loops you have, the better off it is. So this one's not attached to anything yet, so I wouldn't make any current if I attach this to something. I don't know if you can see it. But in my hand, I have a magnet. This is actually a cow magnet. And you can look up why they're called cow magnets. But basically, and I think they still use these, and I don't know if it's the same type they use, but farmers, ranchers make cows swallow these things, and cows have like, I don't know, 3 or 4 stomachs. Maybe you know what this is. But when they're young, they make the cow swallow this, and it stays in that first stomach, because cows, when they're out in the field, they pick up wire and nails, and they don't want the cow's intestinal tract to be damaged by all that metal. It could kill the cow. So this magnet sits in that first stomach and gathers, especially if the cows are in the field, gathers those metal pieces and stays there. And then when the cows are processed to make hamburgers and steaks, they take these back out and then they resell them, I guess. Actually, I know this because, well, you can look it up, but my grandfather worked at a meat packing plant, and he took me on a tour one time, and they showed me how they process cows. It wasn't fun, but then he would give us these magnets. So this one actually probably came out of a cow. It's been cleaned up, but anyways, it's good memories of my grandfather. But cow magnets. Anyways, they're pretty good magnets. Now they're not made of neodymium. They're like some kind of iron material. They're good magnets, but better magnets make this more efficient. This is Commonwealth Edison's bread and butter. This is how they make electricity. They make it much more efficiently than I'm going to do, but basically if you take a loop of wire and you just either move the loop of wire or move the magnet through that area, you're making electricity. I probably wouldn't even be making enough to light up a little bitty light bulb, because the name of the game to make this useful to other people is you got to do it efficiently enough to sell it so that it doesn't cost you more money to make the electricity than it is to sell the electricity. But certainly there's plenty of people that want to buy electricity. We like electricity in our house. But basically, this is the basic idea. This is all the Commonwealth Edison does. Well, they don't go like this, okay? What they do is they take the coil of wire, big coils of wire, and they spin them. That's much more efficient. So basically, they need an energy source that spins their coils of wire. So they basically put their coils of wire on like turbines or something like that. And the way they spin these things is either they put them in windmills on hills. That's a good way to do it. Put on windmills, and windmills then have fan blades, and they take the energy out of the fan, out of the wind, and they spin a coil of wire by a magnet, and it makes electricity. Right? Or they have water go over a dam, hydroelectric. The water goes over the dam and hits a paddle wheel. The paddle wheels are connected to these big coils of wire, and they call them generators. They generate electricity, make electricity. But the more common way to do it still is you could burn coal. Basically, there's still some of these. We're trying to get rid of it because it pollutes the air. You burn coal, and basically they heat up a big pot of water, a boiler, and they turn the water into steam. And the steam blows over a turbine, these fan blades, and it spins the coil of wire. So basically that's an energy conversion from burning coal, heating up the water, turning it to steam. The same thing. They do the same thing in a nuclear power plant. I'm a big fan of nuclear, by the way, and we don't want to necessarily get into all that because I think it's a very clean way. We have to deal with the possible nuclear problems, but those can be overcome, I think. But I don't want to get on my soapbox here. But it's a clean form of energy. You can keep your environment very clean with nuclear. But basically, a nuclear reaction, it heats up a pot of water. It gets hot. They control it so it doesn't get out of control. That's one of the issues. You got to make sure you control it. Don't let it get out of control, and contain it. And you heat up a pot of water. Pot of water turns to steam. The steam blows on a turbine and spins the turbine. Okay, and that's like the effective nature of moving a magnet. That's making electricity. It's not hard to make electricity. Doing it efficiently, then getting it from the place where it's being produced into the city and into your houses, that takes some infrastructure, but we're pretty efficient at it. So making electricity, it requires a moving magnetic field or a moving coil of wire in the magnetic field. So the magnetic field doesn't necessarily have to move because it's harder to move a heavy magnet. It's easier to move the lighter weight coil and to spin it. It's very efficient. All right, so some of the background material. Actually, let me show you a little video first that this actually does work. So what we're going to have here is they're going to hook up these coils of wire to this galvanometer, which we've talked about before, and I'll talk more about that at the end of this lesson as well. But there's a little needle here, and it's going to be used as an ammeter to show when there's current. So he has a magnet in his hand. Well, he's going to hook this up. Can't hear anything here, but he's hooking up this coil of wire, and then he's going to move a magnet, and you're going to watch the needle move the magnet in, out. So the needle goes to the right when he goes in, and the needle moves to the left when he pulls the magnet out. If he does it slow, he doesn't get much of effect. The faster you do it, the more the effect. And what he's making here, he's using a magnet, so he's got to move them. He's making electricity, and he's making alternating current, because when he goes into the coil, the current goes to the right, and when he comes out of the coil, the current goes to the left. All right? But once again, it's inefficient to move the magnet. It's more efficient to spin the coil. But when you spin the coil, you automatically get alternating current. And now we will go to the bigger coil. He's going to hook up the bigger coil. Let me fast forward here a little bit. Let me try to get forward. Okay, now he's got the bigger coil. And now he's doing it, and if he does the same motion, he gets more current. So if he does it fast. So I think you get the idea there. If you move the magnet or coil, or either one of them, you move it one direction or spin the coil, the current goes one way, then the other way, one way, then the other way. You're making electricity. Very simple in practice. To make it efficiently, to sell it, another story. All right, some other related or topics that then mathematically calculate how much current you make. Let's do this equation first. Magnetic flux. So magnetic flux is the flow of a magnetic field through space. Here's the equation. Flux, we use the Greek letter phi. It's a zero. It's like a zero with a vertical line through it. Flux, magnetic flux, is B dot A. It's BA cosine theta, and theta is usually 0 degrees. I'll show you a picture here in a minute. Flux density to the right here. Flux density. that's what we've been calculating before, what we call B fields. If you solve that equation over there, if you let theta be 0 degrees, cosine of 0 is 1, and you solve that for B, you get B equals flux divided by A. So this is the magnetic field. So that's an A in the bottom there. And B is measured in Teslas. That's what we've had before. It's flux over area. It's what we call Webers. Okay, well, flux is Tesla meter squared. We call that a Weber. But we've been doing that before. B, like the previous unit in 22, B was mu 0 over 2 pi I over R, the magnetic field around a wire, magnetic induction. So we've calculated B before, but now here's another way to calculate it. It's flux divided by area. So it's Webers per meter squared, but it's a Tesla. Let me show you some diagrams here. So going back to the idea of flux. Flux is B dot A. BA cosine theta. So this yellow region here, and usually they're going to be circles, a circular coil. But it has a plane. So if the flux is the purple lines, it's the flux, flowing of flux through that area. But how much flux per unit of area is B? It's the Tesla. It's the magnetic field density. We call that magnetic field strength or magnetic field density. If you take this area, though, and you turn it sideways, if the flux is flowing to the right and the area is flat, and we define the direction of an area by a perpendicular to the plane of the area. So here the area vector, the red vector, is up. None of that flux goes through that paper or through that area because the area of the paper is horizontal and the flow of electric field, the flux, is horizontal. So none of it goes through that area. Now there could be an angle here in diagram 3 where you have the cosine of that angle. But in the first case, the direction of the surface perpendicular to the surface is A vector, which is the only case we're really going to do, is we're going to have perpendicular to our area. So the cosine of the angle will be 0, cosine of the angle is 0, cosine of 0 is 1. We'll have either full flux or no flux. That's what we're going to have. We're not going to have these angled fluxes or these angled problems. That's for a future class. Let me give you an example. Well, I'll do an example. Well, here's the example. If there's a flux of 7.6 times 10 to the negative 6 Tesla meter squared, Webers. So you have the flux equals BA cosine of 0 degrees. So it's perpendicular. So it's perpendicular. The flux is perpendicular to the plane of the hoop. It's a circular hoop. That in this case, it's a circular. Actually, this is the size of a basketball hoop. That's what I made. The basketball hoop is 45 centimeters in diameter. But a basketball hoop is usually horizontal. Well, that's how it is in a basketball court. So the Earth's magnetic flux doesn't go through it. You need to take the hoop off of there and turn it sideways to get the flux to go through the hoop because the Earth's magnetic field is horizontal. And the plane of a basketball hoop is horizontal. Its actual area vector perpendicular would be towards the ceiling of the gym. So no flux is going through a basketball hoop. You need to take it down and turn it sideways. But let's just say that's what's happening here. You have, say, a basketball hoop that's sideways, then you turn it flat. Well, we're not turning it right now. We're not going to turn it right now. We're just holding. We have a basketball hoop, something the size of a basketball hoop, that's turned sideways, letting the Earth's magnetic flux pass through it. And we have a flux of 7.6 times 10 to the negative 6. This is a pretty easy substitution problem. We're looking for B. We're looking for the field density. Okay, the flux density. So when they say flux density, they're saying B. If they're just saying flux, they're saying phi. P phi full fum. I don't know why I said that, but A equals pi r squared. All right, so we can calculate the area, 3.14. The radius here is 22.5 centimeters, so that's 0.225 meters squared. So you can get the area of this hoop is 0.159 square meters. It's against the size of a basketball hoop. Not that it's really important because we could have any size loop or conductor, but a basketball hoop is metal, so it would be a conductor. All right, and then you just divide 7.6 times 10 negative 6 by the 0.159. You get 4.8 times 10 to the negative 5th Teslas, which is roughly what the Earth's magnetic field strength is. Once again, we can call that magnetic field strength or magnetic flux or field density. So when we use the word density, we're talking about B in Teslas. When we're just talking about flux, we're talking about phi. Okay, the 7.6 times 10 negative 6. So you got to get used to the terminology here. But if it says density, they're asking for B. That's how much flux per unit of area. All right, now Faraday's Law. This tells us how much voltage we get. And voltage is one of the key players. It goes back to Ohm's law, V equals IR. V equals IR. We want to get voltage, the more current for a given resistor. So Faraday's law says the induced voltage, which will then produce electricity, is proportional to the number of loops and the rate at which the magnetic field changes in those loops. Right? It is, now down here, there's a couple of different ways it's written. It's, I'll put the way I like it, negative n, well, delta phi, that's delta phi, change in flux. You need a change in flux, you need something moving. Delta phi over t. It's change in flux over time. I'll give you some examples in a minute. And n is the number of turns. And a lot of times it's just one. Like that basketball hoop example we just did, it was one. And the reason why I used the basketball hoop, because if you write this all out, and we'll come back to why it's a negative. The negative really isn't that important for us. But we'll talk about that in a minute. But we'll leave it in there because it traditionally has the negative in there. It's negative, I put it like this, delta n b dot a, or ba, over t. So now you can maybe see how, if you're into basketball, NBA. That's the version I like. Negative delta NBA over T. Delta means something changes. Either the number of loops change, which typically doesn't. Your coil has 10 loops and you don't change the number of loops you have. But B is your magnetic field strength. That can change. Or the area can change, but usually it's the magnetic field strength that changes. Or the amount of area that's exposed to the magnetic field density, B. Okay, divided by the time. A lot of times they'll put delta T in the bottom here. You don't need to put, you can put a delta T, but we're going to kind of ignore the delta T. It's a time period, delta T. It also comes back to the Hall effect equation, the E equals BLV, which we'll come back to. But I also want to remind you that we also have V equals IR. That's Ohm's law. Technically it's delta V. We're going to use that again. And V and E are the same thing, or delta V. Once again, I could go back to this equation over here to the right. Delta V. We drop the delta. Even in the E equals delta NBA over T over delta T, actually the delta there is way more important than even over here. It's important everywhere, but a lot of times we get sloppy with this. But over here, we almost never leave the delta off of there, and I'll show you why. And once again, not to confuse you, but this is how the books work. E is voltage, potential difference. It's technically delta V in all these cases. It's delta V. All right, before I do an actual numerical example, let me tell you why the negative is there. It's important in practice, and we as physics people, myself as a teacher, we kind of overkill this, because basically the negative is there to tell you which way the current flows. Clockwise or counterclockwise. There's only two directions the current can flow. Or it doesn't flow at all. If you're not moving anything, if you're not changing anything, there's no current. So I'm going to spend a lot of time on something that really has a simple answer, either clockwise or counterclockwise. But this is a three-dimensional issue that you kind of think through. Basically, Lenz's law tells you which way the current flows, clockwise or counterclockwise. And they use these, not fancy words, but the words that are used are the sense of the induced EMF. Well, when they say the sense, it means the direction of flow. Does the current flow clockwise or counterclockwise? And if it's actually not connected to a circuit, the current doesn't flow at all, but it wants to flow. Which way is the voltage? Which way is the voltage? That's why they say the sense of the induced EMF. because if there's no connection, there's no current flow, but it wants to flow. Which way does it want to flow? It wants to flow the way the current is induced. And here's the thing. Here's the kicker. The induced voltage opposes the change that causes it. In other words, EMF doesn't like change. So Lenz's law tells you how much voltage is going to be produced, which will cause current. So you can measure the current according to Ohm's law. But Lenz's law tells you which way the current will flow. So here's the deal. Like in this green example, this first example over here. When you take this magnet with the North Pole, and these blue lines represent the magnetic field of that North Pole, away from the North Pole towards the south. But the idea here is this. If I take this magnet and shoot it into this loop, this single conducting loop, where this side of the loop is closer to us than the back side. So when you put that magnet in there, current will flow. And it shows you in the diagram the current's going to flow, according to our perspective here, counterclockwise with this three-dimensional diagram. But if we're on the left side looking at this, that's going to be a counterclockwise direction. But they gave us the answer already. All right? Because what happens is when the current starts flowing in that green wire, it induces this magnetic field, which was last unit, the B equals mu 0 over 2 pi I over R, the induced magnetism. So this magnetic field right here, this little arrow, black arrow loop, it's coming around in front of the wire and going back behind the wire. So my red arrow is going behind that wire. But this red loop that I just drew is the magnetic field induced, or the magnetic field that is produced by the wire's current. So with all these problems, there are two magnetic fields. There's the magnetic field of the wire, of the magnet, that's the blue. So what we're doing is I'll change the blue. So what the magnet is doing is it's putting magnetic field into the center of loop that way. And there wasn't any magnetic field to begin with. So what happens is current starts to flow in the loop, in the coil, the conductor, that is going to be the opposite direction. So now the magnetic field around that wire is actually a circle, but if you look at the tangent to that circle, not outside it, but inside it, the tangent to that circle is this way. Oops, let me change the different color. Change to red. So the tangent, if you take this circle around that wire, according to the right-hand rule, RHR2, right-hand rule number 2. They're showing you that with that person's hand right there on the wire, on that green wire, with your thumb pointing in the direction that the current has to flow in order to create a magnetic tangent, okay, that I just drew here in red. This is opposite the blue. It's opposing it. That's why the current has to go in a direction that it's shown in that arrow to create the magnetic red flux circling the wire. It induces that the current is flowing to induce that magnetic field that opposes the blue field that's being introduced from the magnet. Let's do another example. So that's how we know that the current's going counterclockwise in that green loop. But now in this example over here, all right, it doesn't show you which way the current's flowing, but it's giving you some of the answer. So once again, you're using a north pole, and you could use a south pole. If it's a south pole, all these black arrows here would be pointing in the other direction. All right, but if you take this magnet and you shoot it into that loop, and this is closer to us. This point is closer to us than this point back here. So that point back there is further from us. So I'll put a red dot on here. That's closer to us. That red dot is a portion of that wire that's closest to us. The question is, from the right-hand side here now, will the current go counterclockwise or clockwise if we're looking at that loop of wire from the right-hand side? Okay, well, what's going to happen is, and I'll change to blue again, so you're going to put blue magnetic field into that loop, changing from black to blue, okay, just to be consistent with the first example I did. So I'm putting blue magnetic field in there. So once again, now the current in that wire has to be created such that it opposes that magnetic field coming in there. So it's going to create magnetic field, okay, according to the right-hand rule number 2, such that we get magnetic field to the right that opposes that. So I'll switch back to red. Okay, red. So I think the current has to flow this way. So that red arrow there represents current flow in that wire. If the current flows, no, that isn't the right direction. Because if I grab that, that's wrong. So I picked the wrong direction. Whoops, I lost my blue arrow now. So I'm introducing blue flux from the magnet. The current will flow, the current's going to flow this way. The current's going to flow that way. Because if you put your thumb on that wire and point downward like that, that gives you all those purple lines, that purple magnetism. So they already drew that in for you. Okay, those would be tangents to the magnetic field induced around the wire due to this current that I just drew in there. That represents current. It says B induced. So the B induced is opposite that blue one, that blue magnetic field that's being introduced by the north pole of that magnet. So in that case, but from the right-hand view, if you're on the right-hand side of this, that's also going to be counterclockwise. Now, here's the thing. And now when you pull this magnet out, here's the tough one. Well, it's going to be the opposite answer. The current's going to go the other, because when the magnet goes in, the current goes one way. When the magnet comes out, the current goes the other way, because here's the thing. Once you have that magnet in, if you put that magnet in that loop and you hold the magnet in the loop, then the current would stop flowing. You got to keep moving the magnet. So if you put the magnet in the loop, that's when current flows, like we just showed you there, counterclockwise from that perspective. If you stop moving the magnet or the coil, either one, then the current in the loop stops moving. There's no longer any induced current or voltage. But now, once you pull the magnet out, the shortcut would be, well, it's going to be the opposite of when you put the magnet in. But why is it opposite? Well, what happens is when you pull the magnet out, the loop of wire doesn't like change. When you have the magnet in there, you have that magnetic field from the magnet in that loop. But when you pull it out, the current starts to flow to try to put that back in there. So in other words, the current will start flowing this way, which is clockwise from the right-hand view. Because what you're doing when you pull the magnet out, you're pulling away this blue vector. So I just erased it. So you're pulling that out of there. And what the loop wants, it wants it in there. So once it's in there, it wants it to be there. So the current flows to create that kind of magnetic field that produces what was there. So in step A over here on the left, if it's not there, it tries to stop it from getting in there by creating a magnetic field to the right, by having current going counterclockwise in that loop. But once it's in there, it wants to stay there. So if you pull that magnet out, it's pulling all that magnetism out of there. So the current flows, okay, using the right-hand rule, so such that you induce magnetic field that would be like that which was there. So it opposes any change. So that's Lenz's law. To make a long story short, it tells you which way the current flows. It's trying to create what magnetism was there. If it was no magnetism there, it tries to counter what's coming in. If there was magnetism there in the loop, it tries to create the magnetism that was in the loop by using the right-hand rule. Lenz's law tells you which way the current flows in a loop. So let's now apply Faraday's law to an actual situation, an MRI machine. And these will be the much more common problems. There'll be a lot more point values for this on the homework and on test. Lenz's law just tells you which way the current's going to flow in a loop or a circuit. It doesn't have to be a circular loop. But here now we're going to figure out what the actual voltage is that would make the current flow. And I like the particular version of Faraday's law where you have delta NBA. I just like saying that, NBA, over delta T. And a lot of times we don't put the delta T on the bottom there. But this one, pretty much the numbers are given to you, remembering that this EMF is voltage. And we're going to figure out how much voltage is induced here by the change. And there's going to be a change in magnetic field. So pretty much you just substitute the numbers in here. Talking about a person's wedding ring, which is your loop in this case. You're going to have a wedding ring that has no magnetic field in it. And you're going to put the wedding ring into the machine, or it's part of your hand, but your hand is not metal. The metal ring is where the current will be induced. And so it's N equals 1. And well, we're going to find the area of the ring. So the area is pi r squared. I'll do a separate calculation for that. Pi times its diameter is 2.24 centimeters. That's 1.12 centimeters, which is 0.0112 meters. So I do the calculation there, and the area of that, and I did all the calculations here. So the area of the ring is 3.94 times 10 to the negative fourth square meters. It's not a very big area compared to square meters. So I brought that over to the equation, negative delta NBA. N is one loop, one turn, one ring, one circular ring. The B field didn't change, but the area did. The area changed from 0 meters squared to 3.94 times 10 to the negative fourth. That's what changed. You put that total area into the magnetic field when it wasn't there. So that's the change. Then the time is 0.24 seconds. Just hit your calculator and you get the voltage, the potential difference. EMF is 3.4 times 10 to the negative 3 volts. That's 3.4 millivolts. So not a whole lot. There wouldn't be much current flowing in that ring. All right, so here's one though. We have a 25 turn copper coil with a particular diameter. All right, it's another one of these, pretty much a substitution problem. There's a couple extra steps here, but negative delta NBA. Now N here is 50 over delta T. But it says in this case, we got to get the magnetic field density. We got to find B. Once again, B dot A is flux. We don't need to find that, but you could take. We're going to find B, but we got everything else. Although we have to do a side calculation using Ohm's law. V equals IR, technically negative delta V, and so delta V here, it tells you you have a current flowing when this process is undergone. You have 8 milliamps. That's 0.008 amps, and a resistance of 0.078 ohms. So your potential difference, delta V, is 6.24 times 10 to the negative fourth volts. That's the potential difference. That's the EMF. So I'm going to plug that in over here on the left. I'm going to plug all these numbers in, and then we'll do the calculation. And once again, I finished it off. So our delta V was 6.24 times 10 to the negative fourth. The area of this inner part of this coil is pi r squared. The radius is 6 centimeters, half of 12. That's 0.06 meters. So the area is 0.0113 square meters. So that's my area. That's which the flux was going through, full flux to zero flux. So that's the change then is going to be that much area to zero area. And then the only unknown there is B then, because we know 25 turns. 15 milliseconds is 0.015 seconds. That's where the 1.5 comes from there, but you got to convert to seconds. And then, of course, the 6.24 times 10 to the negative fourth, which I determined from Ohm's law. Multiply both sides by 0.015 and then divide by the 25 and the 0.0113. You get 3.4 times 10 to the negative fifth Teslas. Another good test question would have been then to say, okay, how much flux was there? Well, you take that times the area gives you the flux. I'm not going to do that right now. You just take 3.4 times 10 to the negative fifth times the area, B dot A, was the amount of maximum flux at the beginning of the problem. It went to zero flux as the coil rotated. All right, so Faraday's law, basically telling you how much voltage you can create by moving a magnet or a magnetic field by a wire or rotating a wire. It's how basically the process, the conceptual process is making electricity, how we make electricity. That's electromagnetic induction, making electricity, which, like I say, Commonwealth Edison is good at, and people pay money because we like electricity in our houses. We like lights, we like air conditioning, we like our electronic devices that need to be charged. So I'm glad they figured this out.